In this video, we are going to do a deep dive into a DCS and discuss some of the whys and hows associated with a DCS. Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealPars videos. This way, you never miss another one. Let's first clarify for the purpose of this lesson what we mean by DCS. Over the years, the term DCS has evolved from the original description for the acronym as a distributed control system to the use of the term decentralized control system, and they seem to be somewhat interchangeable nowadays. Regardless of which description is used, we are discussing a structure that, at the high-level view, is a system that coordinates and supervises an entire plant of many varying processes. Briefly, as a point of historical review, when PLCs were invented, they were really good at handling single processes, and were primarily used for repetitive discrete control. The advent of the DCS was for controlling many autonomous controllers that handled many continuous operations, mainly using analog control. Through time and innovation, the lines have blurred a bit between the two systems, but each in current day have some principal differences. PLCs traditionally were used for single batch or high-speed control, have a relatively simple low-cost design, and are the core of the system. Their design is flexible and generic, but completely customizable. Processing time for tasks are typically very fast. Operators usually interact and control the system using some sort of graphical display, such as SCADA. A DCS is used for continuous complex controls. They have an integrated control center much like a SCADA, which is the core of the system versus the processors in a PLC system. The DCS has a number of predefined functions that come ready to customize and deploy for various applications. Processing times are somewhat slower. Operators interact with the control system via an integrated graphical display. DCSs also have a claim that when safety is a top priority, the DCS is the most reliable system. The reason for this is because the manufacturer supplies both the control and supervisory equipment as an integrated package. The risks of integration errors are greatly reduced. There are indeed scenarios in which a PLC system would be the best option, such as smaller-sized processes where you could employ redundant components to negate the possibility of process shutdowns. Without redundancy, you risk production halts due to the nature of a single processor controlling an entire plant. Redundancy may be deployed in either the PLC or DCS applications. We will talk more about redundancy in a future video. Just as there are circumstances for a PLC system, the use of DCS would be for larger, more complex processes that require a lot of interaction between many processors. Now that we've touched on some of the differences in the systems, let's focus on the DCS and some of its components. The DCS is a process-oriented system that uses closed-loop control. A typical plant starts with a centralized operator control center, typically called operator stations. Operator stations, in a DCS, are the heart of the system. This is where the operator can observe the operations of the plant, view process warnings and alarms, monitor production, and more. The next level of components may contain servers, archiving computers, and engineering stations. Communications with the operator station level is typically industrial Ethernet. Servers are used for the collection of data at the processor level. They are responsible for the data that moves between the operator station and the processors on the plant floor. Archiving computers are used for storing historical data that may be used for trends or compliance. Engineering stations are used for creating the projects on which the processes run. This includes hardware configurations, logic for tasks, graphical displays for operator interaction, and the administration of all those tasks through installed software packages. This is the station that is used to download the projects to the processors and the graphical displays. At the next level, you have the master controllers that supervise the individual processors as well as I/O modules. These controllers are also responsible for providing the data to the servers, which in turn supply the data for the graphical interface. Industrial Ethernet is typically used for communication with the previous level. Fiber optic may be used here when Ethernet cabling runs would be too long. At this level, the processor executes the logic and does what it needs to do in order to control the process. The next level is the field device level. Communications between this level and the processor level can be nearly any type that may be compatible with the components. Those include Industrial Ethernet, Profibus DP, EtherCAT, fiber optic, or other proprietary communication protocols. Components at this level would be devices such as transmitters, switches, valves, motors, remote or distributed I/O, etc. In short, both PLCs and DCS have their place in the market today. PLCs would work best in a small production environment, where component failure, if no redundant system is deployed, is a small risk for the application, the budget is restricted, or the tasks and I/O count are minimal. A DCS would be better used in an environment where there are large I/O counts, with many continuous processes. A processor failure in one section of the plant is not a problem for production, or risk assessment has determined that an integrated package would be the best option. The line between the two systems is nearly invisible nowadays, and it may not be long before there is no differentiation at all. In future videos, we are going to discuss SCADA and contrast DCS and SCADA systems, so stay tuned. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.